The Transmission Control Protocol, or TCP, and the Internet Protocol, or IP, are two protocols used to move traffic between two nodes on a network. IP is very much like a transcontinental subway system. IP forwards data packets between nodes on the way to the packet's final destination. Some packets may not arrive because a backhoe cut a fiber cable or a node along the path crashed. IP uses best effort to deliver packets. That is, it tries to deliver, but doesn't guarantee delivery. If reliability is needed, IP assumes something else will guarantee that reliability, such as TCP. In a packet-switched network, the decision on where to send the packet next, once it arrives at a node, is called routing. The computer that controls where the packet goes is called a router. The decision of where to send the packet next is made separately for each packet entering the router, even when a flow of packets has already traversed the router between a particular source and destination. Imagine for a moment a subway system with all of the tracks being one line in each direction. Before you get in the subway car, you post a big sign on the front of the car that specifies your destination, such as Chicago. On the back of the car, you place a sign that shows where you are starting from, say, Atlanta. Once you begin your journey on the subway, at each intersection, a subway engineer looks at your destination and directs you to go down a certain track based on your destination, which is Chicago. If many of the tracks between Atlanta and Chicago are not functional, then you will be directed to Chicago via the only route that is open at the time, via Los Angeles. If the tracks are completely closed, then you will be directed to return home with the message that all roads are unusable. At some point, you may get to Chicago, leave the subway car, and arrive at your destination. The router performs tests on the packet to ensure that the packet has not been corrupted or damaged and has remained intact along its path. The router then retrieves the destination address from the packet and performs a routing table lookup. When the router is doing the lookup, it is looking for the best match in the routing table for the destination. The router then hunts through all the entries in the table looking for the best match. A match is found and the packet is sent along the path to the computed best next hop. In the event that no match is found, then the packet is returned to the sender with an error. Many routing protocols are being used in networks to propagate reachability information about all of the destinations in the Internet. 3 types of protocols used on the Internet include the Routing Information Protocol, the Open Shortest Path First Protocol, and the Border Gateway Protocol. The Routing Information Protocol, or RIP, is a distance vector protocol. In essence, this protocol computes a distance and direction to each destination from where it is located in the network. This is much like a signpost on the road, where the sign specifies both the direction and the distance to the destination. If there is more than one way to get to a site, the router will forward the packet along the path with the least cost, or the path with the least associated distance, in this case, 2. However, when the router is faced with 2 equal cost routes to a destination, depending on the node, the router would use both, or pick one of the routes. RIP works by sending an advertisement every 30 seconds containing information about all known remote networks. If RIP hasn't heard an update about a network within 3 minutes, it will time out the route and remove it from the routing table. RIP also thinks in hops, or a jump across a node on a journey to a destination. If you see an advertisement for a route that is 6 hops away, then you can expect for the packet to traverse 6 nodes before reaching the destination. RIP only has a hop count of 15. 16 is considered infinity. That is, there's no way to reach that destination. In today's Internet, considering 16 hops to be unreachable is pretty unrealistic, considering that it may take a packet 30 or more hops in its journey from Europe to Australia. That is why RIP is only used within small networks. In contrast to RIP, the Open Shortest Path First Protocol, or OSPF, is a link state protocol which lets the router look at a complete map of the journey before the packet leaves the terminal and then pick the best way to reach its destination, rather than following the signposts, as in RIP. At each hop along the way, each router will give the packet an updated map, and it will look at the map again and make sure that it is still following the best path. When Open Shortest Path First protocol is first turned on within a router, it will listen for other routers running OSPF. The other routers running OSPF will advertise the fact that they are still around by broadcasting a hello message every few seconds. If after 10 seconds there is no response, the router will assume the silent router has died, in which case it removes all routes that have the defaulted router as their next hop. OSPF will only send information about networks whenever a router reboots, or once every 30 minutes, whichever is sooner. OSPF will flood new routing information as soon as it knows about any changes, for example, if a router has been added or rebooted. A group of routers running OSPF will form a community. Within the community, each of the routers knows about the others and where they are in the network. Each of these communities is called an OSPF area. One special area in particular is called the backbone area. This area interconnects all other network areas together. Different companies or people control each of the smaller networks which form the global Internet. For convenience, we refer to each of the smaller networks that fall under separate administrative control as an autonomous system, or AS for short. Thus, each of the networks that connects to the Internet is a separate autonomous system.